Great. Okay, very excited today. Mark Miller is here to present uh, the guidance computer on the Apollo moon missions. Mark has participated in the development of a number of scientific database and data modeling technologies, including Silo, ASCII DMF, HDF5, ITAPS, and the MAC SIO. Forgive me if I said any of those wrong. Scalable I/O proxy application. Mark has been a lead developer of Silo since the late 90s, supporting scalable I/O requirements of LLNL HPC simulation codes, including AL3D, CUL, Aries, LASNIX, Overlink, and Visit. Mark's expertise includes data models and their impact on software interoperability, high-performance I/O, software quality engineering, smart libraries for HPC libraries. Mark is passionate about the history of computing and the role of inclusion in the success of scientific computing projects. Thank you for being here, Mark. Very excited to hear your talk.
Sure, thank you. Thank you, Stephanie. I'm going to go ahead and share.
Okay, and while you're doing that, I just, as far as questions in the chat, feel free to drop your questions in the chat. And then if you'd like, more real-time interaction, there'll be some opportunities to, let Mark know we have some questions. So we'll start the chat.
Hang on, I keep on doing the wrong thing when I share here. Okay. Are you seeing my presentation mode?
Yes, looks perfect.
Okay, great. Okay, thanks, Stephanie, and thanks everyone for coming. So yeah, we'll talk about the Apollo guidance computer today, which is a really interesting computer effort in the 1960s. So this is a little outline of what I'll talk about today. I'll give just a little bit of background. I'll talk a little bit about the hardware architecture of the machine. I'll spend probably most of the time talking about the effort to develop the guidance software for the Apollo missions. I'll talk a little bit about the historical context in which this work took place. And then we'll get into some mission applications at the very end. I'll at least cover how the computer handled Apollo 11, which is a really interesting story, which is the first moon landing. But there are interesting stories in literally every Apollo mission in which the computer played a role. First thing I'll say is landing on the moon is really hard. First country to actually, impact the moon at all was Russia in 1959. And by the mid-60s, both Russia and the US had successfully soft landed on the moon, but we'd made a number of attempts and had a number of failures. And then it was quiet for about 50 years. And then China successfully was the third country to soft land on the moon in 2013. And then more recently, 3 different countries and a commercial company have tried to soft land on the moon, and all of those have had marginal success. One might even say failures, and all of the failures have been related to software, which is kind of interesting, the guidance software. So why look back at a half-century-old computing effort? Well, so for me, computing history is inspiring as well as entertaining. I also think, a lot of times when I'm confronted with a problem, I say to myself, somebody's got to have solved this problem already. Let's go see what they did. And so I often look to the past to inform how I'm going to do business. And then the other thing that I notice quite often is the more things change, the more they stay the same. So also, just this is me from when I was a kid. I was really enthralled with the Apollo program in the 1960s. I used to build ST's rockets. I flew a lot of model aircraft, and of course, I sometimes played being an astronaut when I was a kid. So you will notice in this presentation probably a lot of common themes, at least I hope you do. Things like co-design challenges, checkpoint restart capabilities, performance portability is actually, I think, a very relevant topic back in the 1960s. Domain-specific languages and the role and impact of non-volatile memory, for example. So these are some of the references I used in learning about this. The book on the far left there, Apollo Guidance Computer, I don't know where I encountered that, but once I got my hands on that book, I couldn't set it down. I don't know if that says more about how nerdy I am or just how good of a book that is. But there's an online project called the Virtual Apollo Guidance Computer as well. The code for the Apollo Guidance Computer is actually on GitHub. And then I wrote a series of articles on the Better Scientific Software site about the Apollo Guidance Computer. So that's it with background. We'll talk a little bit now, get into the we'll get into the background of sort of what led to the space race. So this is a picture of Sputnik being launched on October 4th, 1957. That sort of triggered the space race between the US and Russia. By 1961, the United States had committed itself to the Apollo program. So this was a 10-year project starting in 1961 to land people on the moon. There were 7 crewed lunar missions between 69 and 72. 6 of them succeeded in landing, 1 did not. That was Apollo 13. And the Apollo guidance computer was a critical 4th crew member in all of these flights and was instrumental in their success. So for a little bit of context here, we'll look at computing in the 1960s, the state of the art. The machines were really, really big. They weighed a lot. They took up a lot of power. They weren't super reliable. The mean time between failure was on the order of weeks. When they needed to reboot, it would take minutes, 30 minutes or more to reboot them. The interfaces were very simplistic, and they were down around 1 flops per watt. For context, that's the Livermore Advanced Research Computer 1 in the basement of Building 117 in 1960. So by 1966, MIT and Raytheon had designed and manufactured this computer. The copper housing there on the left is the machine, and the display and keyboard there on the right was a relatively novel electroluminescent display. It was about a cubic foot in volume, weighed 70 pounds, 55 watts of power. The mean time between failure was astronomical, 5 years. It could reboot in 7 seconds. It had a very, very novel user interface, used priority-based multitasking, and it was up 2.5 orders of magnitude faster in performance than the machines of the early 60s. So this is the entire Apollo rocket. The spacecraft are on the very top of the rocket there. There's basically 2 spacecraft. The command and service module there on the left and the lunar module on the right. And each of them are sort of broken into two pieces. The lunar module has its descent and ascent stage, and the command and service module has the capsule itself. That's the only part of the rocket that can safely re-enter, and then the service module with all the additional fuel and everything else. So the main engines, those large bells on the bottom of the spacecraft are the main engines. The 2 that the black arrows point to could actually gimbal around a bit. The computer could gimbal them, and they had variable throttle. The one that the white arrow's pointing to, that's the ascent stage of the lunar module. That had no variable thrust and it didn't gimbal. That particular engine had to be super reliable, and it would just get them back up into orbit from the lunar surface. These little thrusters you see all over the outside of the spacecraft were little attitude control thrusters. They could basically change the orientation and rotation of the spacecraft. So there was a computer in each spacecraft, one in the command module and another one in the ascent stage of the lunar module. If you were in the command module and looking at the control panel, you'd see the little disky there down in the lower left. So that's what the astronauts would sort of punch on that keypad, and it would display back to them with this electroluminescent display what it was doing. And that's it in the lunar module there in the middle of the control panel. In the lunar module, the astronauts would stand to either side of the center control panel there, and they'd be looking out those triangular windows when they were flying it. So what was the role of the computer?
Traveling through hyperspace ain't like dust and crops, boy. Without precise calculations, we'd fly right through a star or bounce too close to a supernova, and then it'd end your trip real quick, wouldn't you?
Yeah, I'm a bit of a Star Wars nerd too. So the whole role of the computer was to manage the state vector of the spacecraft. So that's the position and position rates, attitude and attitude rates. And to do this in real time, accurately, reliably, and continuously. In addition to do it autonomously. And I want to focus on autonomous just briefly. Back in 2019, Tesla, dealing with the autonomous driving problem, decided the only way that they were going to really lick that problem is create their own processors. And so in 2019, they created their own computers, were doing their own silicon to do automated driving, which is a relatively simple problem. It's 2D surface and speeds below 150 miles per hour. So the computer had the challenge of managing the state vector, but it also faced a number of other challenges, such as sensor noise and bias, the moon's lumpy gravity field. The moon is not homogeneous. It actually has mass concentrations, which creates a very lumpy gravity field to fly through. One of the more interesting things is the changing center of the mass as the fuel sloshes around in the tanks. So this is a picture from inside a upper stage of a Falcon 9 rocket, the second stage of the Falcon 9. And you can see while the thrust is moving, all the fluid is in the bottom of the tank as it should be. But once the engines turn off, now it just floats around in there. And so the question is, what's the center of mass of the spacecraft? How does the computer deal with that? So an example of the kind of maneuver that the computer would need to do is when the spacecraft arrives at the moon, as it's traveling from the Earth to the moon, if it doesn't go into a braking phase, it will go past the moon and just continue off into deep space. So it's got to basically go into orbit around the moon. And in order to do that, it's moving at about 2 miles per second. It's 60 miles from the surface. If you're going to try to solve this problem, doing round trip guidance from a computer, land-based computer, it's 2.5 second round trip signal. And of course, on top of that, this particular insertion burn to go into orbit around the moon has to happen on the far side when you're out of communication with Earth anyways. So it's a rather difficult maneuver that the computer needs to be able to do. So that's sort of the background of the computer. And now we'll get into hardware architecture. So that's a picture of one of the first integrated circuits, an integrated circuit flip-flop in 1961. So the machine was designed by MIT Instrumentation Labs. It was also called Draper Labs back in the 1960s. And that's an actual telegram from NASA to MIT to let them know they have won the contract back in 1961 to build the guidance system for the Apollo program. And down there at the bottom it says, covering the first year is an estimated 4 million. In today's dollars, that might be 40 to 45 million. It was manufactured by Raytheon. Both Raytheon and MIT had combined efforts before to develop the guidance system for the Polaris missile. That has relevance to Livermore Labs, of course, because we developed the warhead for that missile. But it was the first computer to be fully implemented with integrated circuits. NASA went to a number of manufacturers, Texas Instrument, Westinghouse, and so forth, and finally settled on Fairchild. They had a very, very rigorous testing system to test for the integrated circuits to see if they would actually survive space flight. So they ultimately selected Fairchild. The machine had a 16-bit word size, 15 useful bits, 1 bit for parity, 1 megahertz clock. Instructions were broken down into a 12-step microsequence, 7 steps of which was the memory cycle. There were 4 central registers and a number of special purpose registers. These were all implemented using 2800 integrated circuits. These were dual 3-input NOR gates, sort of a flat pack. That's an example of one of the circuits and a rough estimate of their size scale. And that's an actual purchase order from MIT to Fairchild Semiconductor. It says in Bedford, Massachusetts there, but their actual manufacturing facility was out in Sunnyvale, Santa Clara area, which basically was the area that became, we now know as Silicon Valley. By 1966 or 67, this effort was consuming about half of all the integrated circuits being manufactured in the country. So for the memory, there were 2K erasable words for erasable memory. This was implemented using coincident current core, which was a very common memory technology of that era. What's really fascinating about this machine is they had 36K words of fixed memory. This was also implemented using cores, but it's woven rope core. And the way that works is you have an array of donuts, magnets, and you weave a wire through a core for a logical 0 or around that core for a logical 1. So you can literally knit a bunch of 0s and 1s into an array of cores. It's highly reliable memory. And this is actually a picture of a Raytheon worker doing just that. You can't see the wire that she's threading through that array of cores, but she's basically knitting into that array of cores a program. Eventually, they hired an army of women in the Massachusetts area to do this. They were all experienced textile workers. And then eventually they even got better and had computer-assisted weaving. So both erasable and fixed memory were non-volatile. And by the way, this is all the memory that the system had, 76 kilobytes of memory. There's no files, no tape backup. Everything that they need to do to run an Apollo mission needs to fit in that memory. So if you take that copper housing, sort of cut it in half and open it up like a clamshell, this is what you'd see inside. So that's basically all 2800 integrated circuits forming the CPU. And then the rest of this is fixed and erasable memory, timing, and I/O channels to the various devices on the spacecraft that the computer needed to control. The machine was originally designed with the notion that maybe the electronics would not be super reliable, and the astronauts would have to field replace different components midway through a flight. So it was basically designed so these modules could be removed mid-flight and replaced with a working module. Turned out they never needed that because of how reliable it was, but that particular aspect of the design stayed with it through the entire program. So it had 4 central registers, standard things like the accumulator, program counter, Q and L registers for doing division and multiplication. A number of special purpose registers like shift registers. You could write data to a particular shift register and it shifted it up or down by so many bits. 8 basic instructions and 33 extended instructions. This is an example code snippet. The opcodes there are in red. You see 2 extended instructions there and a bunch of basic ones, extend RAND and extend BZF. What's kind of interesting about this snippet is the comments, which are basically the software engineers, explaining why this particular, function call is being made and what it means for the astronauts, for the crew. So right after the basic hardware was designed, the next thing they developed was something called the interpreter, basically a virtual computer to run on that computer. And you can think of this like a space guidance domain specific language. It's also kind of a little bit like a P-code machine or a Java virtual machine, but it basically had its own virtual register set, virtual accumulator, program counter, and so forth, and it had a small stack. And they could do with this, single, double, and triple precision vector loads and stores, adds and subtracts. They could do square roots, dot products, normalization. And the whole point of this was it was a much more reliable way to develop the guidance software. And in particular, it really served as a form of compression to express the guidance software. So this is an example of interpreter code, the instructions you see on the far left, going down the far left, to do the calculation in red up there, which is a vector z is the scalar a times the matrix m times the sum of 2 additional vectors x and y. And that whole calculation required 7 words of storage and when it was expressed in the domain-specific language of the interpreter. So the numerics, whole numbers, integers, they had 16-bit words, but they had 1's complement, and it was big Endian. So they had 1 bit for sign, 1 bit for parity, 14 bits of magnitude in there. And then for fractional numbers, basically the same thing, except the bits represent the halves, the quarters, the eighths, the sixteenths. So that represents the mantissa. And what happens is any particular block of code, the exponent, for the particular number had to be assumed. It was implied by that block of code. That's very much the way an engineer's slide rule works. Is you basically keep track on a separate paper, the exponents, and the slide rule allows you to maintain the precision. So again, single, double, triple precision operations there as well. And those are the times for add, multiply, and divide. That those times probably don't make as much, are not as useful as this particular diagram. So this is showing 3 different computers. The Apollo guidance computer in blue. And in mid-60s, IBM released the IBM 360, which was an amazing machine for its time. That's in orange. And then the IBM AC922 system, which is basically like our machine here, or Summit or Oak Ridge, and various metrics that are relevant to spaceflight. So maybe flops per kilogram or flops per cubic meter as far as how much space. And you can see the blue bars there are quite high relative to the IBM machine of the same era. So it was a pretty impressive machine. As far as the operating system goes on it, it sort of had two kinds of jobs it would run. Really, really tiny jobs it called tasks, and those were managed by something called the wait list, and then long-running jobs that were priority scheduled. So a job of higher priority could basically get in front of and disrupt jobs of lower priority. Sometimes all a task would do is turn around and start a job. The computer also supported something called waypoints and restarts. So critical guidance routines were restart protected. And so what would happen is periodically through the routine, it would save its state to erasable memory. And then a job could be restarted. If the machine rebooted, it would have particular pre-programmed rules on how it would restart the jobs during a restart. And this whole feature of the computer consumed about 4% of its fixed memory. And there was a memo written in NASA in 1968 to sort of ask the question, why are we doing this? We should get rid of this feature. It's costing us too much in memory. And the truth is, if this particular feature hadn't existed, Apollo 11 would not have landed. So the I/O devices on the two computers had to handle. On the left there is the command module and all the different devices the computer interacted with. Lunar module on the right. The things in green here, the way that they talk to the computer is through interrupts. So they say, I have some data, talk to the computer runs an interrupt service routine, gathers the data from that device, and then goes back to whatever it was doing before it was interrupted. That's for fairly low bandwidth interactions. One other thing I should say is there are substantial differences, of course, between the two spacecraft. So, for example, the lunar module has a landing radar. The command module, of course, didn't need that. It also has a rendezvous radar. So there are major differences in the way the two spacecraft, in the hardware the two spacecraft needed to control. The other kind of devices were high bandwidth devices, and they used a technique called cycle stealing. So the way that works is the program counter's marching along, and it gets to a point, and a device out there, a cycle stealing device, says, stop, don't do anything more. I want to control the bus. And so the program counter just comes to a halt. The computer's not doing anything. And the external device is routing data over the bus to memory. And that was, for example, landing radar and various other small, some of the other devices on the system. That's relevant in the Apollo 11 landing as well. So the machine had fault tolerance incorporated at many, many levels. You know, it could detect power glitches because it's doing priority scheduling. The way that works is it has to ask the question every so often, is there a more important job than the one I'm running right now? And the way it would do that is there was a particular memory location called new job, and it should be reading that every 960 milliseconds. And so there was timing circuitry in the computer that if that location was not being read every 960 milliseconds, it would conclude something's wrong and restart itself. That also is relevant on the Apollo 11 mission. So it was extremely reliable. As I said, NASA had a very comprehensive test program for the integrated circuits. It would subject them to thermal loading, to vibration loading. It would bathe the integrated circuits in an all nitrogen atmosphere for several days and then let them sit in a vacuum. And if they outgas nitrogen, they declare those circuits are not good. They had a very rigorous testing program for how good the integrated circuits were. So they calculated the mean time between failure at over 40,000 hours. There were no hardware faults observed in any of the actual missions. So that's it with the hardware. I guess I can pause there if it makes sense, Stephanie, if there are any questions that came through.
So far, no questions in the chat.
Okay. Thank you. All right, so we'll move on to the guidance software, which for me is even more interesting than hardware. That's a picture of Margaret Hamilton. We'll talk a little bit more about her later. So MIT received a contract based on just a very short requirement statement. Requirements started changing at the very beginning of the project, and they just continued to change throughout the project. So midway through the Apollo program, the AGC was completely redesigned, and so they had two systems, Block 1 and Block 2. Block 1 they used in all the uncrewed test flights of the Apollo program, and Block 2 in the crewed flights. The effect of this is these two machines were different enough to program that it essentially doubled the software effort for the whole project. In 1961, when MIT received that memo, that telegram from NASA saying, you've been selected, none of the hardware you see in these pictures was known. In fact, NASA didn't even know how it was going to land on the moon at the time. Ultimately, NASA settled on something called Lunar Orbit Rendezvous to land on the moon, and that was where they have spacecraft undock, go down to the surface, and then come back up and dock again. But this was a really revolutionary idea. So none of the software or hardware was known when MIT started designing the entire guidance system. So this is an extreme co-design challenge. And this is an idea of all the different contractors that needed to interact regularly in order to develop the system. And of course, this is the 1960s. I don't even think they had email at the time. So they were using maybe telephone and fax and other ways of interacting. I'm really glad that we have the collaborative development tools we have today, because this would be a nightmare to try to work in. Okay, so what was the software deliverable that software developers needed to produce? They basically needed to produce a flight program. And in fact, that there is the Apollo 12 code listing. And they needed to give it to Raytheon to start weaving the cores 2 months. They needed about 2 months to weave the cores. They got faster at that as time went on, but about 2 months, and then 2 months to install in the spacecraft for the crew to run, tests and crew rehearsals and so forth. And they needed to do this for, at the time, what they believed to be 30 planned flights, some with very unique guidance requirements. So how do you write the software for flying to the moon? The really big question is delta V. In space flight, it's changing the velocity. Anytime you need to change the velocity. So they divided the mission into phases by velocity changes. So a lunar mission to the moon is divided into about 11 major burns of the main engines to change velocity. This was a super diagram developed by NASA in the 1960s about what a lunar mission looked like. So what we say in the AGC, we had an app for every burn that the AGC needed to perform. And in modern parlance, we'd say, oh, yeah, we have an app for that. But back then, they called it a major mode program. So I'll give you a little example of development of some of the software, how they developed some of the software. One thing that the computer needed to know is, where is the moon? What's its position and velocity at any time? That's probably an important question for a guidance computer to know the answer to. Excuse me. So this problem had been studied a lot. And what they needed to do is basically have it woven into the rope cores of the computer months before the actual mission, so that when they were flying the actual mission, they knew it would basically know the location of the moon during that 2-week period that a mission lasted. So they would use land-based computers to basically predict where the moon was going to be. They get highly accurate data for that. And then they develop a polynomial fit to that. And it's that polynomial fit that would ultimately be put into the fixed memory in the machine. And then there's the subroutine you could call that would basically run that polynomial fit at any moment and tell you where the moon is. So that's basically the kind of activity that would go on in software development for the guidance computer. I mean, you can imagine many, many different routines. Another routine was using fixed star locations. They had a catalog, I think, of about 15, 20 different key stars in the sky. And they essentially had a space sextant that they could use to focus on those stars and help orient the computer if they needed to, for example, make a correction in its guidance. So there was a lot of infrastructure produced early on. I've mentioned early the executive and the wait list. They needed something to send telemetry down to the ground so that all the ground controllers could see what all the different values were. For example, how much fuel was in the tanks or so forth. The restart capability, all these different features of the computer took up some number of words in fixed memory. So by the middle of the 1960s, most of this infrastructure software was taking about 22% of fixed memory on the machine. So I'll talk a little bit about the autopilot. So this is how, when the engine's burning, the main engines are burning, how does a computer make sure, for example, that the thrust it's producing is going right through the center of gravity or the center of mass of the spacecraft. And you need to be able to do that for a number of different configurations of the spacecraft. So this is a common configuration that the spacecraft are in. This is a different one, yet another one, yet another one, yet another configuration. And that particular configuration is when they're doing reentry, which has ballistic properties to it and lift properties as well, which the other configurations don't have. Finally, this funky one, maybe you can put it in the chat if anybody wants to take a guess. This particular configuration only occurred on one Apollo mission. I should be looking at the chat if I say that. So let me just bring chat up real quick. I wonder if anybody wants to venture a guess what mission that was. You can type in the chat if you happen to know. Okay, that was Apollo 13. It was the only mission where that configuration Nonetheless, software engineers had already kind of anticipated that something like this might be needed, and they actually had guidance software even for this configuration. So the question to ask yourself is, how do you write a piece of software, the digital autopilot, that handles all of these different configurations of the hardware? That's, in my opinion, that's a performance portability challenge. So what they did was something called Kalman filtering, which involves two phases. The Kalman filter algorithm makes a prediction. There's a prediction phase based on an idealized model of the spacecraft. And then there's actual sensors, for example, the inertial measurement unit on the spacecraft that can tell it what its actual position is. And it compares the predicted from actual, and based on that, it will come up on control decisions for the thrusters and for the main engine. And this is just an example of one of these control decision curves for, I think, coasting flight and whether or not to fire an attitude control thruster to keep a spacecraft oriented correctly. So it was one piece of software, the digital autopilots was a large piece of software, but the question is, how did they handle a lot of different configurations of the hardware? And so that was basically a set of parameters that were sort of input to the software. So you saw those control panels. The astronauts would go through a checklist when they're going to do a burn, you know, turn this switch that way, turn this switch that way. And what they were doing is setting up some of the key parameters that the computer's going to use to run that burn. For example, over there on column E, they could enter into the computer the rate, how fast they wanted the spacecraft to be able to rotate during this particular burn, anywhere from 0.05 of a degree a second all the way up to 2 degrees per second. So they'd get all that stuff entered, and then they'd hit the go button, and the engine would burn following those parameters using the digital autopilot software. So this is kind of what it looks like in terms of breaking down where routines existed in fixed memory versus erasable memory. You can imagine erasable memory that stored all the parameters for all the different instruments and position and stuff like that, and fixed memory stored all of the main routines, digital autopilots, that sort of thing. Eventually they did in some Apollo missions actually radio up to the computer erasable memory programs. So they'd send code up and then would stick it into erasable memory. They did that on Apollo 9, for example. They did a ton of testing. There was a huge testing effort. Testing just cost more and more resources. They never really could have enough test resources. And they even did tests with the computer in flight. So for example, I mentioned Apollo 9 mission. The Apollo 9 mission, the lunar module flew in Earth orbit. They wanted to test the lunar module, but they did not want the lunar module to decouple from the command module in case there was a problem with it, because then they couldn't get the astronauts back from it. So the way they tested the lunar modules with the spacecraft docked together. And it was because they had guidance software in the computer for that test is why Apollo 13 was able to make a number of the burns that he needed to make to get back home, because it was in exactly that configuration, and it was the lunar module that was doing those burns. But in this test here in Earth orbit, they discovered that they were not modeling a particular aspect of bending mode of the spacecraft correctly. So there on the left, you see what their the actual outer gimbal in a solid line and what their simulated outer gimbal angle, engine gimbal angle was in the dash line. And obviously those are hugely different. Once they come up with a new model, then you get the answer on the right there, where the dotted and dash lines don't match up perfectly, but they're a lot closer. So this gives you some idea of the total FTEs involved and some of the breakdown of the names of the software. So on the left there, everything below the dash line is for uncrewed flights, and they had somewhat creative names for all of those releases. But by the time they got into the crewed missions, NASA did not like all the different names they were coming up with for the software. So they called the Lunar Lander software Luminary and the command module software Colossus. And then up there in the upper right is sort of all the FTE efforts that went into each of the releases. Honestly, you can't even see it. I wouldn't expect you to read it. The Apollo 11 release is somewhere over right here, I think, is Apollo 11. So by the time they got to Apollo 11, they had most of the software nailed down. These curves here, in fact, I think I have, yeah, okay. So that green line is representing all of the effort that went into development of the hardware. So it peaked around 65, and by then they were pretty much done with the hardware. That line there is a software effort, and that continued to grow to over 350 people in 1968. So a lot of people working on the software. This is some idea of what the system cost. The software effort alone in 2019 dollars would have 500 million overall, about 100 million a year is what they were running for the software. And this is some breakdown of the difference, whether they're talking about documentation, management, testing, coding, so forth. I don't know too many projects that spend 25 to 30% of their budget testing. So that's a lot of testing. Just some quotes from some reports that I found online. The need for formal validation rose with the size of the software. Programs 2,000 words took 50 to 100 test runs, and full flight programs 1,000 to 1,200 runs. So a lot of testing. This is another thing that I found fascinating in regarding the software development effort. No one doubted the quality of the software. It was the process used in development that caused great concern. It's like, how are they developing that? One of the things that I was astounded by is, I'm using auto documentation tools today. I like auto documentation. The less I can write, the better. The more that it just sort of comes out of the code that I write, the better. They were basically dealing with an auto documentation problem in the 1960s as well. Another obviously very important thing, requirements need to be clearly defined and carefully managed. And I think that continues to be true of software projects. So that's it for the software effort. Now I want to spend a little time talking about historical context, but I'll pause if there were questions. I don't see any in the chat. Oh, I see, Patrick, you'd answered Apollo 13. For whatever reason, I wasn't seeing that early on, but thank you. Okay, so we'll skip into historical context real quick here. Okay, so I'm just going to go through a number of pictures real quick, just showing you different people involved. If you were going to spend time online looking at information about the program, these are the kind of pictures you'll see. So these are the Mercury 7 astronauts. This was a program that was before Apollo to get experience in space. These are the Gemini astronauts. That was another program that preceded Apollo. These are some of the leaders of the development of the Apollo guidance and navigation system. These are all of the Apollo astronauts. These are the people in Saturn launch control. This is where down in Florida, where they actually launched the Saturn from. This is Apollo mission control. These are the only people that ever walked on the moon. And this is what major television news coverage at the time looked like. So if you're spending time doing research about it, you might conclude that the only people involved in the project were white men. And you have to dig a little bit deeper to find some more of the details about it. So one of the things that I found fascinating as I was looking into this was learning about the Mercury 13, which this is the title of a Netflix documentary. I think it's the title of a book also. If it's still on Netflix, I highly recommend it. But the people that were testing the Mercury astronauts for physical fitness and aptitude for space flight decided, let's test some women too. So all 13 of these women were pilots at the time, and they made it through the exact same program that the Mercury astronauts went through to basically demonstrate they had the same aptitude, and in many cases even better for space flight, at least for the tests that they had defined for space flight at the time. Nonetheless, none of them got their chance to be astronauts. The first woman in space was put into space by Russia in 1963. That's Valentina Tereshkova. The next woman put into space was also Russian, but not for another 20 years after that. And then the United States put their first woman into space in 1983, Sally Ride. So I'll continue this a little bit and talk about women in computers as well. So if you look at the word computer in human history, going back centuries, it didn't refer to a machine until the mid-1900s. It referred to a person who calculated. And so calculation was often considered tedious work, and it was a human computer. If you look at the history of human computers, were almost always women. In fact, on the Manhattan Project, they used the term kilogirl to refer to the number of women that they were going to have to put on a particular calculation. But before 1960s, computers were almost exclusively women. So I'll just go through a set of pictures here. I think this group of women is helping to determine the orbit of Halley's Comet to basically predict its return. This is Oak Ridge, 1942. That's Manhattan Project. Los Alamos, also Manhattan Project, 1943. This is Bletchley Park. This is in Britain, 1944. This is the effort to break the German Enigma codes during World War II. JPL. This is Langley West Computing Group. So these are the women that are featured in the movie Hidden Figures, which I love that movie. That's just a great movie. NASA 62 there. So you think with a lot of the women involved in these early pioneering efforts in computing that we would just continue to see more and more participation in by women in computing. The red line in this plot shows computer science degrees by women, and it sort of peaks basically around 1985, and it starts to drop off, whereas other things like medical school and physical sciences continues to approach parity. So we still have a lot of work to do there, I think. Within the Apollo Guidance Computer Project itself, I've learned about a number of women. I've talked about the women who helped manufacture it there in the upper right. A number of women were actually involved in the software effort. Margaret Hamilton, who I'll talk about in a minute, she was a leader in the development, but a number of other women were involved in the actual guidance software itself. Phyllis Rye, Elaine Dennison, Sadine Zeldin. Margaret Hamilton she was the lead developer on the lunar lander software. That's the software that we used to actually land on the moon. And she's credited with coining the term software engineering, which I look at myself as a software engineer. I mean, I understand I have degrees in computer science, but I think of myself as a software engineer. And she introduced that term to bring the software effort legitimacy, so that it and those building it would be given due respect. And that's a number of different flight programs that she's standing next to there for the different Apollo missions. There was one woman in Saturn Launch Control. Her name is Joanne Morgan there on the left. And then one woman also in Apollo Mission Control, Frances Northcutt. I also learned a number of men of color in the project as well. So William Mallory there on the far left was a test engineer who worked on the project through the 60s. Ramon Alonso, his family immigrated to the U.S. from Argentina in the 1930s, and he was a lead hardware architect of the AGC. Robert Pinckney was hired in the late 60s to also help on software development. And then there were two astronauts, selected astronauts, Captain Ed White and Robert Lawrence, who were ultimately going to be in the manned orbiting laboratory program. But that program ended up getting canceled. The last person I want to talk about, and as far as the Apollo program, I don't think you can talk about it without talking about him, is von Braun, Werner von Braun. He was the creator of the V-2 rocket in World War II. He was a member of the Nazi Party, but he was arrested by the SS for suspicion of loyalties. He was captured along with a number of other scientists and brought to the US in 1940 at 45, as it turns out. And it turns out that those people were basically being brought to the US in 45 while we were still holding tens of thousands of American citizens of Japanese descent in internment camps. But Werner von Braun led the development of the F1 engines, which is the booster to the Saturn booster, which without that booster, we would not have been able to land on the moon. He ultimately became a promoter and advocate of racial integration in Wallace's, Alabama. And I just found this short video of him talking about a program being rolled out at the Manned Space Flight Center.
Orientation and training today is directed towards that end. If we at Marshall are to have an affirmative program, one that will place the center above reproach, your assistance, your affirmative attitudes, and your dedication to a principle that is based upon what is right, what is just, and what is fair will be needed.
So I just think that particular story arc is very interesting. Of course, since then, the shuttle program, we've put into space a number of people of different ethnicities through the space shuttle program, which is great. If you watch a lot of the online space stuff like I do, you see a number of different organizations, Rocket Lab, SpaceX, Blue Origin, talking about their space efforts and the people that that are hosting that. That's great to see. I'll just end this section with sort of juxtapositioning a set of photographs from 1968 and another set from 2020. Basically, and this gets back to my earlier statement, is the more things change, the more they stay the same. I was stunned to find out in 1968 there was actually a pandemic, the H3N2 pandemic, going around. You can look into that more online, but these pictures just resonated with me, and I thought I'd include them for sort of comparing and contrasting these two errors. Okay, let's see, moving on, I'll talk a little bit about applications. I think what I'll do is I'll talk about the Apollo 11 mission and then stop for either questions and if we want to go into other missions, we can. So landing on the moon is actually kind of this really sophisticated ballet of 3 planetary objects, the Earth, the moon, and the sun, and then 2 spacecraft, the command module and the lunar module. So there's a lot of moving pieces, and it's the very interesting ballet. So there's the Earth and the part of the moon it can basically see and communicate with. Typically, they want to land in places where the sun is very much on the horizon. You don't want to land with the sun directly overhead because it's going to be really, really hot. So what would happen is that in their orbit around the moon, they would essentially drop the lunar module to a more elliptical orbit on that green line there. And so what would happen is they'd burn the lunar module engine for a little bit to adjust its orbit, and then it would come to within 50,000 feet of the lunar surface there as it came around the front of the moon. And if they did nothing at that point, it would just continue on that green line around its orbit. But otherwise, they would actually start their landing burn. Eventually, they would use ground tracking stations. As they came around from the backside of the moon, they used ground tracking stations to figure out where they were. And then based on the information they got from those tracking stations, they'd crunch the numbers on ground computers for a while and then send up to the astronauts before they started their descent, or roughly when they got into their descent, a slight correction in their landing position. And this is what allowed them to land within a few hundred feet of their intended target. That was not true in Apollo 11, though. Apollo 11 did not have that capability. And so this is where they'd start program P63. So there's basically 3 major mode programs involved in the landing. Initially, the astronauts would be flying face down to land, and then it would rotate over, and then they'd start identifying spots on the surface to land. So there are 3 different major mode programs, P63, P64, and P66, to ultimately land. Each one of those programs was providing more automation to the astronaut or more control to the astronaut to decide what they were going to do. And P66, the final landing stage, the astronaut has quite a bit of control. Early on, the computer's in complete control. So the Apollo 11 landing itself, the lunar landing, it faced a number of challenges. So there were communication issues between them and Houston. And the reason for this is they added these blast deflectors to the lunar module at the last minute because they were worried the attitude control thrusters, the blast from them, were going to damage the lower stage. But they didn't anticipate the effect of those on the communications with Earth. Another problem is they started to overshoot their landing by 6.5 kilometers. So this is the picture, high resolution imagery of their landing site in the last minute of their track in that bigger inset. They were supposed to land where you see that red X flashing, but they ended up going about 6.5 kilometers down range of that. In later flights, like I say, they were able to correct this problem. There were program alarms going off. So their computer in the middle of their landing restarted 4 times. I think it was 4 times because of different alarms that they were experiencing. If you read online about what was happening, people will claim that the computer malfunctioned or that Aldrin had a piece of hardware turned on that he shouldn't have had turned on. None of that is correct. What happened is, months, maybe even years before the system was even assembled, there was a bit of information missing from documentation between the landing radar and the computer. They were supposed to be connected in power, what's called phase locked power, so that both systems were following the same phase in power, and they were not, and this was not documented. The effect of this is that the landing radar is trying to tell the computer what its position is. I'm sorry, not the landing radar, the rendezvous radar is trying to tell the computer information at the highest rate it possibly can. And remember, it's using cycle stealing. So it's pausing the program counter and taking control of the bus. And it was interrupting the computer at the rate of 12.5 kilohertz, as opposed to a much more leisurely rate, would have been under 1 kilohertz. So this prevented the computer from doing all the work it was trying to do. and it restarted and picked up where it left off 4 times while they were landing. And I just think it's stunning that Armstrong and Aldrin maintained their cool while that was happening. So it was landing in a boulder field, so that's basically an artist's rendition of what Armstrong was seeing in the last minutes of flight. They're probably at about 1,000 feet elevation there, altitude, and those boulders are the size of houses, and he needed to fly it over that to a safer place to land. So they landed with about 15 seconds of fuel left. Shortly after they landed, there was a threatening ice clogging a fuel line, and they might have to immediately take off again because they were worried there might be an explosion. That problem corrected itself. There were a number of other things that happened on their landing, including a Russian probe that was landing within hours of them landing on the moon in roughly the same part of the moon. So it's an interesting story, but I think I see that we have just about 7 minutes left. There's a number of other stories about how the computer was used in other missions. The Apollo 14 story is just an amazing problem where they basically hacked the computer to work around a problem with the abort switch. There were actually 4 computers in Apollo. So the two I've talked about are the guidance computer and the command module and the lunar module. There was also the launch vehicle digital computer that basically boosted them up into orbit and got them on the translunar path to the moon. That was developed by IBM. And then there was an abort guidance system on the lunar lander as well. That was a backup, basically, in case the main computer failed. And that was developed by TRW. By 1968, the Russians had decided, hey, look, we're not going to be successful in our aspirations for lunar landings and so forth without our own computer. So they developed a computer as well, and it's remarkably similar in capabilities and features to the Apollo guidance computer. And it was first used in an uncrewed mission to go around the backside of the moon and come back in 1968. It was successful. So computing played an essential role in all aspects of spaceflight. This is some early finite element models that they used. It was used in information management for subcontractors and vendors, as you can imagine. It was used actually to help assemble the rocket itself and make sure that they had all the connections connected properly. Obviously used in astronaut training. It was used for mission planning, tracking, weather forecasting. So the Apollo program both drove innovations in computing and benefited from them. And advances in computing definitely helped the U.S. to leap forward in the space race. And that's it. I'm happy to answer questions or talk about other missions if you'd like. But I appreciate everybody staying with me through it. I think it's a fascinating topic. So if you have questions and you'd like to unmute and ask or type in the chat, that's fine. No questions? Oh, thanks, Eric.
It's a fantastic talk. I don't necessarily have any specific questions. I just, I really enjoy this talk. I think it was great.
Sure. Yeah, I don't know if people can vibe with this, but when I look at things people were doing, 50 years ago, I was like, oh my God, how did they do that? I just get completely fascinated with what they did, how they did it. And then I find out, oh, well, what am I complaining about with all these great tools I have? All right. Well, again, thanks, Tom. Yeah, thanks everybody for joining me, and have a good rest of your week then.
Thank you, everyone, for being here. And thanks again, Mark. That was fantastic.
All righty. Bye-bye.
Bye.